Welcome my friends, welcome to my next lecture. Now in my last lecture I started the concept of complex sequences, convergent sequences, and of course if I have a sequence of complex number or series of complex number, then the meaning of convergence of sequences and series. Then I have discussed if I have a, instead of sequence of complex numbers, if I have a sequence of complex functions, then what sort of convergence I have. Or if I have a series of complex functions, then I have discussed what is called pointwise convergence, uniform convergence, because as I said earlier also, I need those kind of concepts to talk about the notions of power series. So my plan for today's lecture is that I will just once again recall the convergence of the series of complex functions. I will just recall like that there are kind of pointwise convergence or uniform convergence, and there is a Weierstrass M-test. That means by some sufficient conditions you can have the convergence of series of functions. Once I have that notions, then you will see I will talk about, or I will introduce the notions of power series, because power series is nothing but a series of functions. Now since I will deal with series of functions, so beforehand I need to know the convergence of series of functions. So for today's lecture my plan is to introduce what is called power series. Then once I have a power series, then couple of properties I will talk about power series, and then at the end you will see if I have a power series expansions around a point, then it will give an analytic functions, and if I have an analytic functions at a point, then it will have a power series expansions. This is if and only if. And then you will have very beautiful theorem that is called Taylor series, and finally I will talk about what is called Lorentz series. So that's the plan for these weeks. Okay, so as I said, I just recall the definitions of uniform convergence of series of functions, because pointwise convergence and uniform convergence of a series of functions is nothing but the pointwise convergence and uniform convergence of a sequence of functions, but this time I have to deal with sequence of partial sum. That's it. So that's what it is. So what is the uniform convergence? So if I have a functions fn from C to C, so maybe if I go back, yeah, so it is absolute convergence I have talked about. So okay, so let me just I should start with this one. So pointwise convergence. What is pointwise convergence? So start with the functions fn. Start with a series of functions where series, each member of the series is a functions, complete valued functions. Then I will say that this function converges pointwise to a functions S. So that means I have to deal with the pointwise convergence of some sequence of functions. And what sequence of functions I will talk about? You consider the sequence of partial sum, that means S and Z, which is k from 1 up to n fkz. This is sequence of partial sums, and if it converges pointwise to a functions sz in D. So that's kind of pointwise convergence of a series. So that means to talk about the pointwise convergence of a series, what you do, you go to the sequence of partial sums, have a sequence of functions, that means sequence of partial sums functions. If that sequence of functions converges pointwise to a functions S, then I will say that my series of functions fn converges pointwise to a functions S. And this is the way of writing S of z is equal to n from 0 to infinity sum f and z. And I already discussed this example, because if I start with z to the n from say 0 to infinity, then this is actually you can have it for e. So if I fix a z naught, which is a unit disk point, that means mod z less than 1, z is in C. Then what is that? So that means this series boils down to this series z naught to the power n, but since z naught is in D, so therefore you will have modulus of z naught is strictly less than 1. So therefore by geometric series you can have it, this will implies, and this is nothing but 1 plus z naught square, so on so forth. So this is, you can have it 1 by 1 minus, sorry, z naught. And prove it there. How to prove it? So proof I also discussed. So to have this sum is exactly equal to this one, you first consider what is called sequence of partial sum. What is the sequence of partial sum? S and Z, which is k from 1 up to n z naught to the power k. And what is that? 1 plus z naught square up to z naught to the power n. Then I can write this one 1 minus z naught to the power n divided by 1 minus z naught, right? That you can write it. Okay, you can do that. So then what will happen? I need to check the convergence of this sequence of functions. So therefore this is Sn of z naught, you can say. So what is that? This is limit n approaches to infinity, Sn of z naught, that means this is limit n approaches to infinity. But since modulus of z naught is less than 1, so the numerator this goes to 1, so therefore denominator is fixed, so therefore this is 1 by 1 minus z naught, okay, and that is exactly, and this is true for all z naught inside this, so therefore this series is exactly equal to 1 by 1 minus z. Okay, so therefore this is very kind of straightforward to prove. If I deal with this kind of functions, fnz is equal to z to the power n, where d is my open unit disk, then the series, this series n from 0 to infinity, this series converges pointwise. And what is the pointwise convergence limit? This is sz, which is exactly equal to 1 by 1 minus z. Proof is very simple. You just take the sequence of partial sums, write it of this kind of form that you know from your technique, real analysis technique, or some telescopic sum, whatever it is. So this is exactly equal to this expression. Then you use the fact that modulus of z naught is strictly less than 1, so therefore z naught to the power n converges to 0 as n approaches to infinity, and it will give you that sum over n from 0 to infinity fnz, which is exactly equal to 1 by 1 minus z. That's the pointwise convergence. Then you will have what is called absolute convergence. Like if I have a series, what is the meaning of absolute convergence? Series of complex numbers. So if I have a series of complex number, absolute convergence means if the series whose elements are absolute of n, that means this series of converges absolutely means if I consider this series sum over n, and if this series converges, then I will say that my series converges absolutely. Same thing if I have a sequence fnz, and I will say that this sequence of functions, of course first there are two, either sequence of functions converges absolutely and series of functions converges absolutely. So if I start with a sequence fnz, this converges absolutely to a function g if for each point z naught, what you do, you consider the absolute of that sequences. That means you consider the sequence whose members are absolute of fn of z, and if this converges pointwise to a function g of z naught, then I will say that my sequence of functions fn converges absolutely to a function g. So that means to talk about the absolute convergence, instead of dealing with the sequence fn, you should deal with the sequence absolute of fnz. And if this series converges pointwise to a function g, then I will say that my sequence fn converges absolutely to a function g. So that's what it is. This is the series, and what about this is the sequence, and what about the series? I will say that a series, if it converges absolutely, that means instead of dealing with this series, I will deal with this series fn of z. And I will say that when this series converges pointwise. Now to talk about the pointwise convergence of that series means what? I have to go to the sequence of partial sum. So go to the sequence of partial sum, that means k from 0 to n fk of z. Now if this sequence of partial sum, if this converges pointwise to a function t, let it be t, then I will say that this series of function converges absolutely to a function t. So that means to talk about the absolute convergence of a sequence or of a series, you have to deal with the sequence of functions. Like if I have a sequence of functions fn, then you should deal with the sequence of functions absolute of fnz. And if I have a series sum over n from 0 to infinity or n from 1 to infinity fnz, then you have to deal with the series sum from n from 0 to infinity or n from 1 up to infinity absolute of fn of z. If these sequences and series converges pointwise, then I will say that my original sequence fn or original series sum over fn, that converges absolutely pointwise to the corresponding functions. So that is the meaning of absolute convergence. That means instead of dealing with the original sequence and original series of function, you should deal with the absolute value of that sequences or absolute value, take the absolute value of that functions and deal with the absolute value of that series. So something, it's like that actually, same concept, but instead of dealing with the functions fn, you should deal with the functions, you should deal with the sequence absolute of fnz, or instead of dealing with the series sum over fn, you should deal with the series sum over absolute of fn, and then talk about the corresponding pointwise convergence. Okay, so now come to the what is called uniform convergence. That is very nice because this is very strong convergence. And what is that? It says that, as I said in my last lecture, so a sequence converges uniformly means, so if a sequence converges pointwise, that means given epsilon, I should find a natural number n naught, and that n naught should depends on epsilon as well as on the point z naught, right? Because if I changes the point, my corresponding numerical sequences fn z naught also changes. So that is called pointwise convergence. But for uniform convergence, given epsilon, you should have the existence of one natural number n, which is independent of the point z dealing with the domain D. So it should be independent of the choice of the point. That means it should depend only on epsilon. And if these things happen, then I will say that my sequence Fn converges uniformly. That's what it is. So we say that let Fn from D to sub D subset of C to C is a functions. We say that the sequence Fnz of functions converges uniformly to a functions f in the set D if given epsilon there exists a natural number n that depend only on epsilon and not on the point, such that if this is true, that means fnz minus fz I can make this is less than epsilon for all n greater or equal to n and for all z. Sometimes since it is true for all z, so you can have supremum of z belongs to D fnz minus fz less than epsilon. That's also you can write it because this is true for all z. Pointwise convergence, this n depends on epsilon as well as point, because if I changes point, the corresponding numerical sequence fnz not changes. But here what I demand is that given epsilon I should have the one single n and which should work for all z. That is why uniform convergence is there. It is uniform over z. So if this is true, this is called uniform convergence. That means sequence of functions Fn converges uniformly. And then what will be the meaning of uniform convergence of a series of functions? Same thing, instead of dealing with series or to deal with the series of functions, you just reduce or you just go back to the what is called sequence of functions. And what sequence of functions you have to deal? You have to deal with sequence of partial sums. So therefore, to talk about this convergence of this series of functions, you just use this sequence of functions Sn, which is sequence of partial sum. If that sequence of partial sum sequences, if it converges uniformly to a functions Sz, then I will say that my this series converges uniformly to a functions Sz in my domain D. Okay. So as I said, this is one of the sufficient conditions for the uniform convergence of a series of functions. This is called Weierstrass M-test. What is that? You start, let Mn be a sequence of non-negative real numbers, let Fn be a complex function defined on a set D with the assumption that Fn of z which is dominated by Mn for all z. That means Fn is uniformly bounded by Mn. So that means Fn of z is dominated by Mn. And suppose you have the extra assumption that sum over Mn, this is a convergent series. If this is the case, then one can check that this series n from 1 up to infinity Fnz converges uniformly and also converges absolutely on D. So I am not going to prove it, but this is a sufficient conditions for the uniform convergence of a series of functions, because later on in some problem, if I want to check that, well, this series of functions I need to discuss whether it converges uniformly or not, maybe that time I will use what is called Weierstrass M-test, and using Weierstrass M-test, the conclusions of the theorem, I can say that my series of functions converges uniformly. So one of the example is this one. Zn converges uniformly on a set D where mod z is strictly less than R. That means I am not dealing with open unit disk. Rather, I am taking R is less than 1. That means I am inside a disk which is sitting inside open unit disk. So that means if I have this open unit disk, this is 1, then I am dealing with this disk where is a disk of radius R, but R is less than 1. In this disk, one can check that this what is called series converges uniformly, and this is also trivial. Why? Because I will use what is called Weierstrass M-test. You see, so that means what series you will have? N from 1 up to infinity, z to the n. That means I can write this is n from 1 up to infinity fnz. And what is fnz? Fn is a map from D. What is your D? Z belongs to C and mod z is strictly less than R to C. And what is that map? F of z is equal to z to the power n. So therefore, I can use Weierstrass M-test to talk about that in this domain, this series converges uniformly. Why? Because you see, since I know my sequence of series of functions Fn, so therefore you can just estimate. So therefore, if I estimate Fn of z, take the sum n from, or maybe just forget about sum, Fnz, which is, what is that? This is mod z to the power Fnz is z to the n. So okay, so this should be Fnz, that means z to the power n. What is that? This is modulus of mod of z to the power n, modulus of z to the power n, right? But z is running over this set D. D means what? This is my set. Mod z is less than R. So therefore, this is less than R to the power n. So therefore, what I concluded is that modulus of Fnz, which is dominated by R to the power n, and that is true for all z in D. And what is my D? All those z is in C such that mod z is less than R. Okay. So therefore, fnz is dominated by r to the power n. So here mn actually what? This is just to compare with Weierstrass M-test. So therefore, here my mn is equal to r to the power n. Now let me see whether this series convergence sum over mn. This is sum over n from 1 up to infinity r to the power n. But this is a convergent series. Why? Because this r is less than 1. Since r is less than 1, this is a geometric series, so therefore it is actually convergent series. So therefore this series is convergent, so therefore sum over mn is convergent. Since sum over mn is convergent and modulus of fnz is dominated by mn, so therefore by Weierstrass M-test, this series converges uniformly on this domain. So this domain is important, because in that domain I have the estimate that absolute of fnz dominated by r to the power n. R is less than 1, so therefore sum over r to the power n is convergent. Therefore by Weierstrass M-test, this series converges uniformly on this domain. Okay, r is less than 1 is very important. Very simple applications of Weierstrass M-test. Okay. So now there is another beautiful results. As I said, that what is that statement of the theorem? Now if you just recall some of the theorem from your real analysis, you see when if you are well known about the sequence of functions and series of functions and their pointwise convergence and uniform convergence in the context of real analysis, you know if uniform convergence is a strong property, right? If a sequence of fn which converges uniformly, that means it will automatically implies that it converges pointwise. But the converse is not true. There are counter examples. Okay. Similarly, in complex setting also, if I have a complex valued functions or sequence of complex valued functions, if it converges uniformly, that means it implies it should converges absolutely, or what is called pointwise convergence, but the converse is not true. That means pointwise convergence is a weak property. Uniform convergence is a strong property. And similarly true for what is called series of functions. If your series of functions converges uniformly, then your series of functions converges pointwise, but the converse is not true. Not only that, there are nice things like you probably remember, if I have a sequence of functions in real analysis, if I have a sequence of functions, real valued functions, and suppose it converges to a sum function, so that means that's what you used to say. So fn is a sequence of real valued function which converges to a functions f, say pointwise. Sometimes this is called a sum function. Okay, sum function. So if it converges pointwise, suppose this is pointwise convergence, pointwise. Now, if each of the functions fn is continuous, but your sum functions f need not be continuous if the convergence happen pointwise. But instead of pointwise convergence, if I have a sequence of functions fn, if it converges uniformly to f, and if all the functions fn's are continuous functions, then you can always conclude that your functions f is also continuous. So uniform convergence preserves continuity of the functions. That means if I deal with sequence of continuous functions, and if my sequence of functions converges uniformly, then the sum function is also continuous. And same thing also true for series also. So now the question I am asking, now since I am already dealing with sequence of complex valued functions, and I know the meaning of the sequence of complex valued functions, pointwise convergence and uniform convergence, and in real analysis you know if all the sequence of functions are continuous and if the convergence uniform, then the limit function is also continuous. Now this time I am dealing with sequence of complex valued functions, and you already familiar with the notions of analytic functions, so therefore I can ask the same questions. Suppose if I have a sequence of functions fn which is complex valued functions, if it converges to a functions f uniformly, and each fn's are analytic functions, this is analytic, because since I am dealing with complex valued functions from some complex domain, so therefore each fn's are analytics, can I say that my function what is called a resulting function or some function which is also analytic? Answer is yes. If I deal with sequence of analytic functions, and if that sequence converges uniformly to your functions f, then your function f has to be analytic. So therefore analytic property is very rigid. So this is true. Now just compare with your real analysis. Now if I have a sequence of functions fn which converges to f uniformly, say real valued function, real valued. If fn's are continuous, then some function f is continuous. Now if fn's are differentiable functions, can I always say that my limit functions f is always differentiable? So this is the question. So the question is, now if I have a sequence of real valued functions fn which converges uniformly to your functions f, each fn's are differentiable, can I always say that f is differentiable? In general, no. So that means if I deal with sequence of differentiable functions and if I have the uniform convergence, then the resulting functions or the sum functions need not be differentiable. There is some extra conditions, if you remember, to talk about the convergence of the differentiations. Like if you remember, I think if I have a sequence of functions fn, say real valued functions, I am talking about real valued functions and to results in the real valued setting. If I deal with sequence of functions fn such that fn x naught, at some point x naught it should converges, that means it converges pointwise at some point, along with the fact that, or if I deal with sequence of differentiable functions such that fn x naught converges, that means fn converges pointwise to at least one point x naught. If the derived sequence fn prime, if it converges uniformly, then your functions fn converges uniformly to a functions f, uniform convergence. On top of that, fn prime is also converges to f prime. So this is like extra assumption. So that means you can have the examples in real valued functions of real variable. You have a sequence of differentiable functions. It converges uniformly to a functions f, but the limit functions need not be differentiable. But to have the limit functions differentiable, I need some extra. What kind of extra things? I can deal with sequence of differentiable functions with the fact that this sequence of differentiable functions should converges pointwise. Not only that, derived sequence should converges uniformly. Then I can conclude that my original sequence fn, which converges uniformly, and the derivative of each fn converges to the derivative of the functions f. That means the limit functions, if I take the, if fn's are differentiable, then the limit functions f, this is also differentiable. That means derivative is also converges to derivative of f prime. So that means in general, uniform convergence need not preserve the differentiability. Like continuity it preserves. If fn converges to f uniformly and each fn's are continuous function, then the limit functions f is continuous. But this is not the case if I deal with differentiable functions, at least in the real valued case. If I start with a real valued functions fn, and if I say that fn converges uniformly to a sum functions f, then I cannot conclude that my function, limit functions f is also differentiable. To have the differentiability, then you need some extra conditions, like if I deal with a sequence of differentiable functions, and if the sequence fn converges pointwise at least one point, on top of that, if I have the sequence of derived functions, that means if I deal with fn prime, if it converges uniformly, then I will say that my sequence, original sequence fn converges uniformly to f. Along with that, fn prime, if I deal with the derived sequences, that is also converges to limit function f prime. Okay, so that means it needs some extra conditions. In general, if I deal with sequence of differentiable functions and if I have that uniform convergence, then limit functions need not be differentiable. However, if I deal with the analytic functions, and that means if I in the complex setting, that means if I deal with the analytic functions, sequence of analytic functions, and I already talked about the uniform convergence of this sequence of functions, then if I deal with sequence of analytic functions, if it converges uniformly to a limit functions f, then this functions f is also analytic, which is not true in case of differentiable functions for real case. So therefore, what my conclusion is that analyticity is a very rigid property. It preserves the differentiability as well. So not only differentiability, it is infinitely many times differentiable. I am talking about it is analytic also. So therefore, if fn is a sequence of analytic functions on a domain D that converges uniformly to a functions f, that is a sum functions or limit functions, then the limit functions, it's also analytic in D. Forget about differentiability, it is analytic there. But this phenomenon, it's no more true in case of real analysis. So that's what I'm saying. Think, what is the analogous result in case of uniform convergence of a sequence of differentiable real valued functions of real value? It is not the case. That means you can have the examples of a sequence of differentiable function which converges uniformly, but the sum function or limit function say need not be differentiable. But however, if I deal with analytic functions in a complex valued setting, if it converges uniformly, then the limit function or sum function always analytic, because analyticity is a very rigid property. So that is why this beautiful things is going on, or it's happening. Okay, so now since I already discussed about sequence of functions, series of functions, pointwise convergence, uniform convergence, now I am in a position to talk about what is called power series. Now we introduce the special type of series. I am writing special type of series of functions. So that is called power series. So unless and otherwise I am not comfortable with series of functions, then how I can define what is called power series. So power series is a series of functions, but this time I am dealing with very special kind of series of functions, and that is called of power series. That means you will say if I have a series of functions and if each term of the series of functions is a special type of function, that means it is a power function, you will see. It is called power series. Okay, so this is the definitions of power series. Look, a power series around a point z0 is an infinite series or is a series of functions. So this is the series of functions, so I can write it as n from 0 to infinity fn of z, right? What is my fn of z? Fn of z is n times z minus z0 to the power n. And what is it? This is a polynomial in z. So therefore now I am dealing with a series of functions where each fn's are polynomial. That's it. So that means I am dealing with very special type of series of functions, and that is known as power series. So definition of power series says that a power series about a point z0 is an infinite series or is a series of function which is of this kind of form. That means it is of the form n from 0 to infinity n times z minus z0 to the power n. Okay, let me see some example. So now once I will have a power series, then you will see I can talk about its pointwise convergence, is uniform convergence, what is the largest domain my series will converge, pointwise or uniform, so on and so forth. So everything will be there. So let me just check one example, very simple example. For example, the geometric series. So this series I can write n from 0 to infinity n z minus z0 to the power n, right? What is my n here? N is 1, z0 is 0. And this series is one of the easiest example of power series because this is of the form this kind of things. Similarly, I have this kind of examples of power series because this also I can write it as n from 1 up to infinity 1 by n z minus 0 to the power n. So this is your n and this is your z0, same thing. Similarly, this is also example of power series, another example. So this is my 1 by 4n is the coefficients n, and what is your z0? Z0 is 3. And z minus z0 to the power n. So these are all simple examples of power series. Okay. Now convergence of power series. Since I am dealing with power series, that means I am dealing with series of functions with a special type of functions, then I can have the convergence, uniform, pointwise, all kind of convergence. Now see, look, see this is a power series I already discussed. Then I am saying that for which values of z this power series sometimes called geometric series, that will converge. So that's the questions I am asking. So as I said, okay, so that as I said, so this you can easily do that because you see this is the formula I was already talking about. Okay, maybe, yeah, so that means z to the power n plus 1. So I was wrong that time. So that means it says that this is the one you should realize 1 minus z to the power n plus 1, that I can write it 1 minus z times 1 plus z square up to z to the n. That means I can write this 1 plus z, so that means this will implies 1 plus z up to z to the n. This sum, it is 1 minus z to the power n plus 1 divided by 1 minus z. I think in my earlier times I said this is z to the power n, so that is a wrong. So I mean it is not wrong. That means here I should stop at z to the power n minus 1 instead of z to the power n. So okay, so that's the kind of mistakes is there. You just kind of make it correct. So therefore, if I have a sum, it start from 1 z up to z to the power n, then I can write this is of the quotients of two polynomials. In the numerator, you will have 1 minus z to the power n plus 1, not z to the power n. That is very important. Okay, z to the power n plus 1 divided by 1 minus z. But anyway, I am only interested in the limit functions. So as long as it is z to the power either n or n plus 1, it goes to 0 since mod z is less than 1. So that from that analysis is okay, but the expression was not quite correct. It instead of z to the power n, it should be z to the power n plus 1. In fact, this is the correct one. Okay. And how to prove it? This proof is also very simple. You see, you have a product 1 minus z and then 1 plus z square up to z to the power n. So what you do, you just 1 times this minus z times. So then what will happen? Cross term will get cancelled. So therefore, if I write it here, this should be 1 plus z square up to z to the n. If I hit it by 1, and then you will have what? Minus z square up to minus z to the n minus z to the power n plus 1. Then what will happen? This will get cancelled. What will remain is that 1 minus z to the power n plus 1. And that's what it is. Very simple expression. So therefore, I can write this 1 plus z up to z to the n of this kind of form. But what is this? This is nothing but Sn z. That means this is the sequence of partial sum of this series. So if I am dealing with series of functions, right? So what is the sequence of partial sum? Sn. This is nothing but k from 0 to n z to the power k. And what is that k from 0 to n z to the power k? This is nothing but this one. And which I can write it as 1 minus z to the power n plus 1 divided by 1 minus z. Now to talk about the pointwise convergence limit, what I have to do? I have to take the limit of s and z, right, as n approaches to infinity, limit. Now you see, if mod z is less than 1, then if I take the limit in that side, left hand side, n approaches to infinity, that means you will have limit n approaches to infinity. In the denominator it is a fixed, it is independent of n, only in the numerator you have to check. But numerator, if I assume mod z is less than 1, then limit of z to the power n is 0, that means limit of z to the power n plus 1 is also 0. So therefore the geometric series converges this 1 by 1 minus. So this is converges to 1 by 1 minus z. At least pointwise it is true. So therefore sum over n from 0 to infinity z to the power n, which is exactly equal to 1 by 1 minus z pointwise. But if I want to talk about uniform convergence, then I have to deal with this kind of domain. So z is in C such that mod z is strictly less than r. In this domain it converges uniformly. And if mod z is greater than 1, then this diverges. Why? Because you see, if mod z is less than 1, this numerator goes to 0. But if mod z is greater than 1, since the 1 by 1 minus z, this is fixed, this is independent of n, so that means I have to only deal with the numerator. That means 1 minus z to the power n plus 1. Now if mod z is greater than 1, that means z to the power n plus 1, it blows up, because mod z is greater than 1. So therefore if mod z is less than 1, it converges. But if mod z is greater than 1, this limit diverges. So therefore this series of functions actually diverges. So therefore if mod z less than 1, limit z to the power n is infinity, that means the numerator 1 minus z to the power n plus 1, this limit blows up. So therefore your series of functions actually diverges. So that is for mod z less than 1 and mod z greater than 1. Now what will happen? Mod z is equal to 1. Now you will see mod z is equal to 1. Of course in this series actually diverges, but you see this point 1, it's sometimes called the, you will see when I will talk about the radius of convergence, this is point 1 is the radius of convergence of the series sum of z to the n. Now inside the radius of convergence it converges, outside the radius of convergence it diverges, but on the radius of convergence, for in general series of functions, it behaves like either it will converge or it will diverge or anything can happen. But you cannot have the concrete conclusion on the radius of convergence. Inside it converges, outside it diverges, that you know. But on the radius of convergence, that means on mod z is equal to 1, there you will do not have any concrete conclusion. Anyhow, these kind of things will be there in my next slides. So let me see. So this is for which values of, so I am asking for which values of z geometric series converges. So if mod z is less than 1, it converges. If mod z is greater than 1, it diverges. That's it. Now I need this concept of limit superior and limit inferior, because you see later on, since I am dealing with power series, you can have the radius of convergence, right? There is a concept called radius of convergence. Now to have the radius of convergence, I need this kind of what is called concept, what is called limit superior and limit inferior. Now if I deal with sequence of real numbers, these are the kind of well-known concept in your real analysis. So I am just recalling it. What is lim sup? This is the notations. Lim sup n approaches to infinity. That means if I deal with sequence of real numbers, you consider supremum of the set n plus 1 and so on. So that means if I have a1, a2 up to n, then n plus 1, then what you do, if I want to find the lim sup, that means you from n onwards you consider the supremum, then it will give you some number, let it be bn, and then you consider the limit of this sequence bn. So what you do, so first you define a new sequence bn, which is supremum of n plus 1, so on and so forth, and then if I have the limit of my sequence bn, then I am saying that this is nothing but the what is called limit superior. Similarly, you can have the definition limit inferior. Instead of supremum, you consider n plus 1 onwards infimum of that set. Let it be Cn is equal to infimum of n plus 1, so on and so forth. And then if I take the limit n approaches to infinity, that's Cn. If this is exists, then I will say that this is limit inferior n. So first one is the limit superior, then is the limit inferior. Okay. So other notations. Now lim sup is also denoted as limit overline. Further, this concept lim sup and lim inf are only for real sequences and not for complex sequences, because you see I am talking about the supremum, na? So if I have a sequence of real numbers, then there is an ordering, then I can talk about supremum and infimum. But if I deal with complex numbers, there is no ordering, so therefore I cannot talk about supremum and infimum there. Okay, so that is why I am saying that it is not for complex sequences. Couple of results, so I am just recalling those things. I am not giving any details of lim-sup and lim-inf, because these are the concepts you are familiar with in your real analysis. So look, so for a real sequences, lim-sup and lim-inf always exist, even if your sequence does not converge. Lim-sup and lim-inf always exist, but it could take the value plus infinity and minus infinity. Okay, it might happen that lim-sup is plus infinity, lim-inf is minus infinity. That might happen, but for a given sequence of real numbers, lim-sup and lim-inf always exist. I am not saying that limit exists. I am not saying limit might not exist, but lim-sup and lim-inf always exist for a given sequence of real numbers. This is the relations. You can have it easily, you can follow, because infimum is dominated by supremum, so therefore this limit have the same respect, so therefore lim-inf is lesser or equal to lim-sup. And the last one is very nice. If I start with a convergent sequence, then the limit of the convergent sequence is same as lim-inf and same as lim-sup. So therefore if I deal with convergent sequences, then lim-inf, lim-sup or lim-inf, it's exactly, or these two values are same, and which is exactly equal to the limit of the sequences. So if n converges, then this properties is true. I need those properties later on. Okay. Another equivalent definitions I am giving limit superior, that is called lim-sup, or sometimes called limit superior. If I have a sequence of real numbers, then lim-sup, this is the definitions I have already given. So this is the same thing, all are equivalent. Okay, this is same as you consider the supremum, and then you will have another set, na? So supremum of AK, so you can say that, say let it be Bn, supremum of AK, K is greater or equal to n, right? So therefore this supremum of AK, K greater or equal to n, it will give you some number Bn. So then what I am doing is that I am considering infimum of the set Bn, n belongs to n. And this infimum I am saying the limit superior. Similarly, limit of these sequences. So all definitions are equivalent. Or sometimes I am saying that you consider supremum of some set E. And what is that set E? Now since I am dealing with sequence n, there are many subsequences are there. So what you do, you collect the set E which are the limits of all those subsequences. So that means if you start with a sequence, collect all the limits of the subsequences, suppose that set is E, if I have the supremum of that set, this is called the limit superior. Because sometimes if I say that, okay, what will be the limit superior of that sequences, sometimes this will be useful to get the value of the lim-sup. Okay, so I have written, so where E is the set of all numbers x in the extended real line, so that means it could take the value minus infinity or plus infinity, such that Ank converges to x for some subsequences Ank of Fn. That means E contains all subsequential limit plus possible numbers plus infinity or minus infinity. Okay, so that means what is my set E? E is the collections of the limits of all subsequences, right? So that means if I have a sequence n, it will have infinitely many subsequences. You consider your set E, which is the limit of all those subsequences, and find the supremum, and that supremum will nothing but the lim-sup of A. For example, you see, possibly, I am saying possibly, not all the time. So if I consider a sequence, say 1 minus 1, 1 minus 1, 1 minus 1, right? So what is the lim-sup of these sequences? Well, these sequences you will have two convergent, two subsequences are there. One is 1, 1, 1, 1, another is minus 1, minus 1, minus 1 is there. So therefore, what is my set E? It should be 1 and minus 1. And what is the supremum of E? Supremum of E is 1. So therefore, lim-sup, so if I take the lim-sup of these sequences An, which is nothing but 1. So sometimes it is called the greatest subsequential limit. That means start with the sequence n, consider all subsequential limit, take the supremum. That means greatest subsequential limit is nothing but the limit superior. Okay. For example, if I have this definition, then I can easily calculate what is the lim-sup of my sequences 1 minus 1, 1 minus 1, 1 minus 1. Okay. So that's what it is. Okay, so as I said, this is the basic convergence results of power series. Maybe this kind of results you might familiar with in your real analysis as well, because if you deal with real power series, then this kind of things will be there. Okay, so what is the theorem? So for a given power series, this is the definition of power series. Define a number R. It could take the value 0 or infinity. And what is your R? So that 1 by R is the lim-sup of these sequences. Now, if I have a power series, then you know what is your N. Now once I have an n, then you calculate modulus of n to the power 1 by n, you consider this sequence. Now this is a sequence of positive real numbers, and I already talked about if I have a sequence of real numbers, then lim sup and lim imp all exist. So if I consider the lim sup, and if I say that this is 1 by r, then this r is called the what is called the radius of convergence. That means you consider if I have a power series, consider the sequence mod n to the power 1 by n, get the lim sup and then reciprocal it, then it will give the radius of convergence, and this is formula is sometimes known as what is called Cauchy-Hadamard formula. Now, so if given a power series, if I define a number r such that 1 by r is equal to lim sup of mod n to the power 1 by n, then the following conditions are true. What is that? So if I take a z, so if I take a z, say this is my z naught and this is a disk of center z naught radius r, in this domain my series converges absolutely, okay, in this domain converges absolutely. If I am in outside, mod of z minus z naught is greater than r, my series diverges actually. And if I take a smaller radius, say let it be r, small r is strictly less than r, in this disk, that means all those z where z minus z naught is lesser equal to r and this small r is less than r, here my series converges uniformly. But you see, I am not saying anything on mod z minus z naught is equal to r. I am not saying on the boundary. On the boundary, you cannot conclude anything concrete. It could converge, it could diverge. Examples I will discuss later on. Okay. So therefore, inside the disk of center z naught radius r, it converges absolutely. That means it converges pointwise. Outside the disk of radius r, it diverges, and if I take a smaller closed unit disk sitting inside the disk of center z naught radius r, it converges uniformly. Moreover, the number r is the only number having the above set 3 properties. So therefore, this r is the unique for given power series, and this number is called the what is called the radius of convergence. Okay. So for this r, you will have these 3 conclusions. Okay. So that's what it is. So continuous from the previous slide. In the previous theorem, the number r which is unique having these 3 properties is called the radius of convergence of the power series. The domain of center z naught or disk of center z naught radius r is called the domain of convergence or disk of convergence. Now you see, on the boundary, that means on the circle of center z naught radius r does not give any information. That means about the convergence of the series, that is called the, on the circle. So if I on the boundary, that means if I on the circle of center z naught radius r, I cannot have any concrete conclusion. That means these are 3 examples I have given, where or later on maybe in my next slide I will give examples where at some point it will converge, at some point it will diverge. Okay, so couple of examples. So therefore, inside I have the convergence, outside I have the divergence, on the boundary I do not know anything about concrete conclusions. So it does not give any information about the convergence. So therefore, I cannot have any concrete conclusion on the convergence on the circle of center z naught radius r. Now this is a power series. So this power series, what is the radius of convergence? You can easily check it. So because what is your an? Your an is what? K to the power n. So what is mod n to the power 1 by n? That means this should be mod k, right? And what is the lim sup? What is the lim sup of mod n to the power 1 by n approaches to infinity? Now this is a constant sequence. So this sequence mod n to the power 1 by n, this is a sequence k sequence, mod k sequence. This is a convergent sequence. Now if it is a convergent sequence, so limit of the convergent sequence is same as lim sup and lim imp. So therefore lim sup is exactly equal to mod k, and which is exactly equal to 1 by r. This will imply r is equal to 1 by mod k. So therefore your radius of convergence is 1 by mod k. If I consider this power series, this radius of convergence is infinity. Why? Again, if I have what is your an? An is what? 1 by factorial n. What is mod n to the power 1 by n? This should be exactly equal to, so n to the power 1 by n. So that means you can say that this is 1 by factorial n to the power 1 by n, right? So this is. Now you see, I want to find the lim sup, right? So look, so that means if I take the limit, so limit n approaches to infinity supremum of this, but this sequence 1 by factorial n to the power 1 by n, okay. So that means this is my sequence mod n to the power 1 by n, right? Now if see what if n approaches to infinity, what will happen? If n approaches to infinity, this series this sequence converges to where? Converges to 0, okay. So yeah, I think this converges to 0. So therefore So therefore lim sup, this is actually 0, but this is exactly equal to 1 by r. So what is your r? So that means r is infinity. So that's what it is. So therefore the sequence mod n to the power 1 by n, which is m as this sequence 1 by factorial n to the power 1 by n. Now if n approaches to infinity, this sequence converges to 0. So therefore the lim sup of the sequence mod n to the power 1 by n, this is 0. 0 is equal to 1 by r, so r is point at infinity. What will happen this power series? So this is, I am saying what I am saying, this radius of convergence is 0. So again, what is n to the power 1 by n, this sequence, if I calculate it, sorry. So this should be what? N is 5 to the power, so therefore you can write this is 5 to the power n square to the power 1 by n. That means this should be 5 to the power n. Okay. So therefore what about this series? Now you have a sequence mod n to the power 1 by n. This is sequence 5 to the power n. Now what is the lim sup? Lim sup of this sequence mod n to the power 1 by n. That means this is lim sup of 5 to the power n, right? Yes, 5 to the power n. Now the sequence 5 to the power n, if n approaches to infinity, it blows up, right? So therefore what will be the lim sup? Lim sup is infinity. So therefore this is 1 by r. So therefore what is radius of convergence is 0, and this is a 0. Okay. So these are the 3 simple examples of power series where you will have the radius of convergence. Okay. Fine. Now you see this is another formula, radius of convergence of the limit of radius of convergence in terms of the ratios of coefficients. Earlier I will have the formula in terms of the lim sup of the sequences mod n to the power 1 by n. Now if I have a power series and if the coefficients is n, then in terms of the ratio of coefficients you will also have the formula. So the radius of convergence of a power series can also be calculated sometimes the ratio of coefficients. That means if I have a series sum over n z minus z naught to the power n is a given power series, then with the radius of convergence r, then this is another formula. I think this formula sometimes will be very useful to get what will be the corresponding radius of convergence. Like the earlier example I have discussed, if I use this formula, it is much more easier to prove, right? For example, like the one, so like this series, 1 by factorial n. So now here n is 1 by factorial n. So that means what is my r? That means this is limit n approaches to infinity, n by n plus 1. That means this should be n plus 1 factorial divided by n factorial. And what is that? This is limit n approaches to infinity, n plus 1, and that is infinity. So very easy. So sometimes this formula will be useful to prove this the second or last one. So n is 5n square, na? So n is 5 to the power n square, right? What is the formula? R limit. So this should be 5n square divided by 5 to the power n plus 1 whole square. And what is that? This, if I calculate it, so that means this should be limit. So 5 to the power n square it is there, and this is 5 to the power n square, then times 5 to the power 2n, then 5, right? So this is get cancelled, and what is the limit? In the denominator you will have 5 to the power 2n, na? So and n approaches to infinity, blows up. So therefore this is 0, r is 0, and this is the case, na? Sorry. This is r is 0. So therefore my point is that sometimes the formula of radius of convergence as the limit of ratios of coefficients will be useful to calculate the radius of convergence. Of course, provided, see I have written, the theorem is that if this is given a power series with radius of convergence r, then r, provided this limit exists, including tending to infinity. So that means you will have the formula provided this should exist. It could be plus infinity, that's okay, but limit should exist. It's not like that if this limit does not exist, then you cannot say anything about that. So this formula will be useful only when you will have the existence of this limit. It could take value plus infinity. So that's what I have written. This is very important. If this limit exists, including the limit tending to infinity in the extended real number system. For example, if I deal with this power series, the earlier example, so as I said, this is limit of n plus 1, so therefore radius of convergence is infinity. Okay, so I think I should stop here. So therefore I have defined the notions of power series, then I have defined what is called radius of convergence in terms of lim sup or in terms of ratios of coefficients of my power series, and then I said that if you are in the inside of the radius of or domain of convergence, what is your domain of convergence? If I have a power series around the point z naught, if I have the radius of convergence is R, then the disk of center Z0, radius R, open disk, this is the what is called domain of convergence. Inside the domain you will have absolute convergence, and if I take a smaller subdomain which is sitting inside of my domain of convergence, that means if I take a closed unit disk of radius small r which is strictly less than capital R, inside this closed unit disk the convergence becomes uniform. In the domain of convergence, convergence is absolutely. Outside you will have the divergence, it's your series diverges, and on the boundary I do not have any concrete conclusions about the convergence. In my next lecture I will talk about couple of examples there you will see on the boundary your series could converge, your series could diverge. So therefore on the boundary I cannot have any concrete conclusion about the convergence. So, okay, so that's kind of maybe next lecture I will talk about that, and then I will talk about more properties of what is called power series, that means sum of two power series, product of two power series, and then I will talk about that if I have a power series expansion around the point Z0, then you will have analytic functions and vice versa. So I think I should stop here. In my next lecture I will start with couple of examples where on the radius of convergence, that means on the circle of center Z0 and radius R, I will discuss with plenty of examples, into 2-3 examples where you will see you cannot have concrete conclusion. Okay, so I think I should stop here. In my next lecture I will start with some examples on the to talk about the convergence on the domain of on the boundary of the domain of convergence. I think I should stop here. Thank you.